From the earliest stages of humankind, we've been explorers. We search for what's past that mountain, what's on the other side of the ocean. We seek out new experiences, new life, and new civilizations. And in the last 25 years, we have pushed that exploration past our Earth in order to discover planets outside of our solar systems. We call these exoplanets. Stars and planets are made at the same time, big balls of gas that combined, they're made of hydrogen and carbon and oxygen, and it collapses in on itself and a star is ignited. But there's extra material that's left over from this expansion. So you get dust, and the dust becomes pebbles, and then they collide and you get boulders, and suddenly you have a planet. But the planet is linked to its star, its sun, not just by what's made inside of it, but because the planet needs the star's light and heat. I study the relationship between planets and their stars in order to find life and figure out what it really takes for a planet to be habitable. But it's really difficult to detect these planets where life like ours can flourish. So we go on 3 different things. First, it's the stars. Then it's the relationship between the stars and the planets. And then finally, the composition of the planets. So first, we need a stable star, one that's not too young, since a planet wouldn't have formed, and one that's not too old, since it would puff up to be a red giant and it would swallow its star. Swallow its planet. And we want a star that's not too active, since it would have flares and they would reach out, hit the planet, destroying any life on it. Recently, the Gaia satellite has observed 9 billion stars. This is the most we've ever been able to observe. It looks something like this, although here I'm only showing you 3.3 million stars. But it's because of all of this data that we're really able to understand the sizes, the masses, and the motion of stars in our corner of the galaxy. On average, we believe that every star has 1 planet. Some might have a lot more, like our solar system, and some might have none. But out of all of these stars, we think that 90% of them are stable planet hosts. But like I said, trying to find a planet is so difficult because they're tiny compared to their host star. It would be like trying to see a human influenced by a raindrop. Plus, planets don't give off their own light, so we have to detect them by the way that they influence their star. So sometimes they pass in front of their star and the light dims. We call this a transit. Other times, the planets create a gravitational wobble. Imagine being gravitationally influenced by a raindrop. Today, we have observed 3,826 exoplanets. You can see them, well, it's about to show, where the blue are from the ground-based observatories and yellow are from the Kepler spacecraft. But we aren't interested in any old kind of planet. Something like Jupiter and Saturn wouldn't work. There's no solid surface. The gas is toxic, and the average person would feel like they weigh 400 pounds. No, we're interested in something smaller, terrestrial, where there is a rocky surface. Something like Mercury, Venus, Earth, and Mars. Next, we need a planet that's at just the right distance from the star for comfortable temperatures. This is called the habitable or Goldilocks zone, because it's not too hot and not too cold. I mean, I barely survive having leather seats in my car. This is also the region where we look for liquid water, since it's so important for life as we know it. We believe that 1 out of every 7 planets, or every 7 stars, has a planet in the Goldilocks zone. However, all of the things that I've been talking to you about have really only to do with the physical characteristics of a planet. I haven't really said anything about its chemical composition, and this means the difference between having a planet like Earth and a planet like Venus, which is made out of carbon dioxide with sulfuric acid clouds and has the hottest temperature of any planet in our solar system. It's hotter than Mercury at 800 degrees Fahrenheit. The Earth's atmosphere is made up of 78% nitrogen, 21% oxygen, some carbon dioxide, and a few other things. So if we found a planet whose atmosphere was similar to this mixture, that'd be great. But too much variation, and we get a planet that's icy, like Hoth in Star Wars. Or we get a planet that has steam instead of oceans. I mean, you thought humidity in Texas was bad. The amount of carbon dioxide that's in our atmosphere is regulated from earthquakes and volcanoes, which happen because of plate tectonics. So this is the moving and the shifting of the plates on the surface of the Earth. However, this motion is then regulated by the temperature or climate of that planet, which in turn is affected by the carbon dioxide. So you see, all of these chemical components of a planet, they're linked, they're coupled together from the inside and out in order to regulate the conditions on the surface. The way that I like to think about it is that the planet's alive. It's moving and shifting in complex ways. However, we've only been able to measure about 20 planetary atmospheres out of the 3,800 known exoplanets. With that being said, I've really just been talking to you about the general definition of habitability. There are a lot of crazy things that make planetary systems really complicated. For example, what if you had a planet that went around 2 stars? What would temperatures be like when sometimes you see 1 star and sometimes you see 2? We don't know, but we've discovered 21 planets with this geometry. And then, what if you had a moon around an exoplanet? We call these exo-moons. Could life actually exist on a moon? We just discovered one a month ago. And then you have extremophiles. These are creatures that love the frigid cold and the intense heat. What about non-carbon-based life, silicon-based life? How would we even characterize that as life? So things are so complicated, and there are so many possibilities. But to tell you the truth, we don't even have the technology right now in order to measure the surface of a planet, to see this life, to see if there's iron and magnesium and silicates for us to walk on. But because stars and planets are made at the same time, we're able to take the elements that we measure inside of stars and put them into models of the planets to look at their interior structure in mineralogy. This is actually what I work on. So while it's a really exciting time to think of habitability, there are also a lot of limitations. I mean, I started off by telling you that there are like 3 million nearby stars that likely have planets. But we can only measure about a handful of them, which have the right star, the right planet, the right distance, the right atmosphere, and that's to say nothing of the surface. But rather than get depressed about the things that I clearly have no control over, I think to myself, we've got to celebrate the victories as much as we mourn the losses. In my personal life, this means that if I do something great, like publish a paper, I treat myself to a huge sushi feast. But sometimes I look to my science. I think of the new advances and discoveries that we've made. Did you know that the Transiting Exoplanet System satellite will be observing thousands of planets? And the James Webb Space Telescope will be monitoring those planets and looking at their atmospheres, really expanding our understanding of habitability. And did I mention we just discovered an exo-moon? It's amazing. There's so much hope in these discoveries. Wonderful steps outside of ourselves that deserve our attention, our celebration, our commemoration. for what we can achieve, not just as individuals, but as a species. There are so many possibilities, so many things to explore outside of the Earth, outside of our solar system, outside of our solar neighborhood. And I don't know about you, but I'm excited for what or who we may find. Thank you.